Welcome to the hidden variables, and today we are going to solve an electrostatic problem. In our problem, we are given the xy plane with a charge distribution sigma x equal sigma naught cosine kx, where k is a constant. We would like to find the electric potential at any given point in space. To begin with, we would like to consider two facts. First of all, that we have translational symmetry along the y-axis, which means that we move back and forth and our solution for the potential will not change. Moreover, it is important to notice that we have periodicity along the x-axis. Having those two facts in mind, we would like to resort to the Laplace equation. The gradient square of the potential is equal to 0. Writing down the Laplace equation in Cartesian coordinates tells us that the second partial of phi with respect to x plus the second partial of phi with respect to y plus the second partial of phi with respect to z is equal to 0 as above. We note that this function is going to be equal to a function of x and z because we don't have y. Using separation of variables, the first line of attack of a physicist, we write this function as a product of two functions, capital X of x and capital Z of z, each independent of the other variable. Plugging back the result into the Laplace equation yields second derivative of x times z plus second derivative of z plus x equal to 0. Dividing the entire equation by capital X capital Z yields negative second derivative of x over x equal to second derivative of z over z. Because the left-hand side does not depend on z and the right-hand side does not depend on x, we know there has to be equal to a constant. We define the constant lambda squared, where lambda is a real number. When we write down the two equations, we notice that those are second-order ODEs. From kindergarten, we know the solutions for the negative sign is going to be sines and cosines, but for the positive signs, we're going to get exponentials. The matching condition along the boundary states that the electric field pointing upwards minus the electric field pointing downwards evaluating on the interface of the surface has to be equal to the charge density divided by epsilon naught. Because the electric field is nothing but the negative gradient of the potential, by writing down the solution to those matching conditions, we can equate the coefficient on the left and or the right hand side of the equation to find out that b, the sine, is equal to 0, a, the coefficient of the cosine, is going to be equal to sigma naught over epsilon naught to lambda. And we know that k and lambda has to be equal. Notice that because the Laplace equation has uniqueness involved, any solution that we found has to be the correct one. So all we have to do is find a solution. Using those coefficients, we can write down the solution. We have a at the beginning, b disappears, and c and d could be absorbed into the constant a. Notice that we have the absolute value on the z to account for the portion above and below the infinite sheet. We can make a check and take the limit as k goes to 0. In that case, the charge distribution will be nothing but sigma naught, which is a uniform charge density. We see that on the exponent we have e to a very small number, therefore we could Taylor expand it, and we see that the first term, the 1, is nothing but a constant without any dependence on z when k goes to 0. The second term, however, does have a dependence on z, and we write it down. Notice that all the other terms contain k and therefore will vanish as k goes to 0. The last step is to take the negative gradient of our result and to recover the electric field of an infinite sheet with uniform charge density. Thank you for watching, stay tuned and subscribe for more content.